Okay, in this lecture we return to talking about series again, and whereas they look like they're just big sums, we can't really treat them like big sums all of the time. And one of the issues we have to be careful with is rearranging. So let's start off with the alternating harmonic series. That's 1 minus 1/2 plus 1/3 minus 1/4, etc. We can easily note that the odd terms of this series are positive and the even terms are negative. And so consider series PQ, so that P is 1 plus 1/3 plus 1/5, and that Q is 1/2 plus 1/4 plus 1/6. And intuitively, we would believe that A is equal to P minus Q. However, we'll show this is not the case. Note that Q is equal to, we can factor out a 1/2 from each term, and it's 1/2 of 1 plus 1/2 plus 1/3, and that's equal to 1/2 of the harmonic series. But from that it follows that Q must diverge because the harmonic series diverges. Now suppose, now note that 1/2 is bigger, that 1 is bigger than 1/2 and 1/3 is bigger than 1/4. So P is greater than Q term by term. Therefore, P must also diverge to infinity. So both P and Q diverge to infinity. That's going to be important. All right, so what we're now going to do is we're going to rearrange the series so that it converges to pi. Okay, and you will see that any number would work here. Since P is equal to P1 plus P2 plus P3, since it diverges to infinity, we may choose N1 so that P1 plus P2 up to P plus N sub 1 is just a little bit bigger than pi. Okay. Now, since Q diverges, we can subtract off some terms of Q before. So we go P1 plus P2, etc. up to Pn, and we go Q1 minus Q2 down to Q sub M sub 1, so that this sum here is just slightly less than 1. Then we'll add on some more terms of P so that it is just a little bit bigger, so it just stops when we get bigger than pi. And then we subtract off so that it's a little bit smaller than pi. And so the terms, the individual terms of P and Q approach 0. Therefore, we will be rearranging, this so that the series we're creating converges to pi. Okay, so because the difference is just so small here. Okay. Okay, we've seen what we can't do with a series of numbers in terms of rearranging. Let's see what we can do. And so let's start out with S, a series of positive numbers, and let T be a rearrangement of S. Then if S converges, then so does T, and they both converge to the same value. Okay, so let's get the setup going here. Say S is S1 plus S2 plus S3 is a convergent series of positive numbers. Let phi from n to n be a permutation of the natural numbers n. We define a series T by letting T sub I be equal to S sub phi of I for I in the natural numbers, and we then put T equal to T1 plus T2 plus T3. We claim that T converges to the same value as S. So let Sn and Tn, with capitals here, be the partial sums of S and T respectively. As S is a series of positive terms, it converges to the least upper bound of the set Sn. Okay. We will then, by an abusive notation, denote the least upper bound of the set of capital Sn by capital S. All right, now let n be a natural number and let capital M be the maximum of the set of phi of I, where I varies between 1 and n. And consider Tn equal to its expansion in the partial sum. This is equal to S sub phi sub 1 through S sub phi sub n. Okay, so at this point, okay, these are exactly equal. Now I throw in whatever S's I need to get this out to these S's to be in a row here. So I'm making it bigger. And so my Tn is less than or equal to S, which is the least upper bound of these partial sums. So the sequence Tn is bounded above by S. It converges, okay. So it converges to something that's less than or equal to S. Now note that S is also a rearrangement of T, and so the sum of Sn, the limit of my Sn's is less than or equal to T, therefore they're equal. That is just so cute.